Well, I wish you were here with me today because you have the potential of winning $1,000. Okay, so how this little game works is we're going to have you randomly choose a starting location on this little money pyramid of sorts, and then we'll turn over the card and look at the card value. Whatever that value is, we'll count that many positions and then turn up the next card. The very last card will be the one that will determine your winnings. In particular, whatever the card value is of that final card, we'll multiply it by $100, and that will be your winnings for the game. Okay, now since you're not here to choose a starting place, I'll go ahead and use a pair of dice to randomly choose that. So why don't we go ahead and we'll declare this to be position 1, 2, 3, 4, 5, all the way to position 11. And so whatever the dice comes up to, that's where we'll start this game. And let's see how you do. Okay, so 5. So we got a 5. So 1, 2, 3, 4, 5. Okay, so this would be your chosen starting place. So let's just see what card value we uncover. It's a 5. Okay, so what that means then is we count 5 over. 1, 2, 3, 4, 5. Turn this one face up. Looks like an 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, what about here? 4. 1, 2, 3, 4. What about up here? A 6. 1, 2, 3, 4, 5, 6. Okay. 3. 1, 2, 3. Okay. 10. Oh, that would have been a nice one to turn up last because you would have made $1,000. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 7. 1, 2, 3, 4, 5, 6, 7. Okay. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, getting down there. Oh, good thing that wasn't your final card. Well, it'd be $100. I guess it's better than nothing. Okay. Oh, wow, look at this. Ace has a value of 1. So we're going to turn this one up. It's a 2. And there's only one card remaining that's still face down. And this will indeed determine your winnings. We'll take that card value and multiply it by $100. So what are we going to multiply $100 by? You tell me. I don't see a card value listed anywhere on the card. I don't know if I should give you a consolation prize for your bad luck, but I guess in the end you can blame the universe because it was the roll of the dice that began this whole process. Okay, so this is a fun little math artifact, or in particular a math effect that takes advantage of the long walk property of sequences in Z sub 11 is where we are. We have 11 cards here, okay? So in Z 11, so this is the integers, modulo 11. This sequence right here has the long walk property. What does that mean? Well, what it means is there's only 2, quote, walks. Now, we just did a really long walk there. We did a walk with 10 steps in it, leaving that one card face down, which unfortunately was the Joker. So a walk is that kind of thing where the value of the card, or the value of the number, tells you how many positions to move in a clockwise direction in the case of how we set up our activity. Okay, so if you land on a 0, you go 0 steps. That means you don't go anywhere. So it's the fixed point. So that's where the Joker needs to be, or whatever card you want to not be turned face up as a consequence of the spectator choosing another card and that card value initiating a walk that ends with this one not turned face up. So this will never be the end point for any walk that doesn't begin here. So all of the other, quote, walks will skip this card here. So theoretically, the spectator has a 1 out of 11 chance of randomly choosing this as their starting location, but that would be equally bad because they don't go anywhere. Okay, so, but most likely they will choose something other than the joker. Okay. So this is an example of a sequence that has the long walk property. So no matter where you start in this sequence, if you do what we've done here in terms of using the current value for the number of steps to arrive at the next value and repeat that, you will uncover all of the cards except for the one that you've placed in the position marked as 0. Okay, so for the very money pyramid that I had set up, I had the joker here, and then if you remember, in fact I can even show you here, but we have an ace and then a 2 and then a 9, 5, 3, and so forth. And if you think about it, it really is just a circular arrangement of a linear listing of values in Z11 that as a group constitute a sequence that has the long walk property. Okay, so I thought I would share this with you. I've shared on my channel already a sequence in Z9 that has the long walk property. Okay, so if you want to look up that video, or I can even put it in the description below. Also, I will include a mathematical paper, a technical paper, that talks about the long walk property and its connection with sequences in Zn having non-trivial sums. So anyway, I just wanted to share this simple effect with you. And once you identify a sequence that has the long walk property, you're really just limited by your own imagination as to how to frame it into a fun routine or challenge for the spectator where you are confident of how it will end, in the sense that either all of the cards in the non-zero positions will be turned face up, leaving that lone survivor face down, or if the spectator is so lucky, they may choose that from the start. And depending on how you construct your routine, that would be an equally acceptable and desirable outcome for you as the performer because of the goal you've set for the spectator. So anyway, thank you for watching, and take a look at other videos on the Absolute Math Magic channel.